Autonomous mobile robots have become a key technology for upcoming planetary missions, namely ESA's ExoMars mission. In contrast with the Mars Pathfinder mission, the actual need for mobility increases in terms of range and duration. In this respect, redesigning specific aspects of the past rover concepts, in particular the development of most suitable all-terrain performances, autonomous navigation, and a power management concept is appropriate. These are the main objectives of the Solaro project. Following a joint VH&S and EPFL proposal in response to ESA's call for innovative technology proposals, the Solaro project proposes a complete study of a solar-powered exploration rover, selected as an element for future scientific missions on Mars. The model mission is to be understood as an example application in order to explore the potential and capabilities of a Solaro-type rover. After landing and deployment, the Solaro needs solar power to move to an area of interest. Then it has to communicate with Earth to estimate with better accuracy its location. The Solaro system-level conceptual design, covering all relevant areas of a regional rover system, in particular, solar power generation and management, mechanical rover configuration and optimization, a pre-study for a flight model, and the development of a Solaro breadboard. Since Solaro uses exclusively local power generation, a detailed Mars environmental study, in particular the available solar power during the mission, must be done. The incoming solar radiation is a function of the date, the latitude, and the atmospheric absorption. With 20% of atmospheric absorption and a solar cell efficiency of 15%, the minimal solar panel size is 0.3 square meters. With mean power consumption less than 14 watts for full-speed movement in rough terrain, the rover will be able to operate during the 4 peak hours around noon. Scientific instrument maximal operation time is about 8 hours per day with 2.5 watts mean power. The Solaro passive structure has outstanding all-terrain performance. To understand the influence of the geometry, the center of mass, and the motor, a Solaro 3D simulator has been made under Sysquake. This simulator returns the forces applied to each wheel, the friction coefficient, and the torque needed to move in rough terrain. The validity of the simulator was confirmed with the breadboard and can be used to simulate the rover motion on planet Mars. Keeping track of position is one of the most important tasks for an autonomous mobile robot. The estimation of the 6 degrees of freedom is critical when operating in an unknown and rough environment such as a foreign planetary surface. The movie shows a trajectory computed online with data coming from the motor encoders, the internal link sensors, and an inclinometer. The Autonomous System Lab is currently investigating methods for long-range position tracking in rough terrain. To fulfill this goal, a probabilistic multi-sensor fusion using redundant information coming from different types of sensors will be used. With this navigation system and the climbing abilities of its structure, the Solaro flight model will fully autonomously reach sub-goals with maximal travel increment of 1 kilometer. The Solaro can be easily set in a launch configuration and deployed. The Solaro breadboard rover has been made of laboratory quality parts components and is, in particular, not space qualified. It is representative of a prospective flight concept system with respect to size, locomotion capabilities, power provision, and payload accommodation. First test is the motion capabilities in a sandy terrain with stone size under the Solaro ground clearance of 21 centimeters. Solaro has no difficulties to overcome this obstacle if the stone edge is under or equal to 90 degrees. The maximal hole the Solaro can get down is about the rover height of 40 centimeters. The spring-suspended fork does not have enough force to maintain the back wheel on the ground. This stability loss can be avoided with a semi-active fork. When the Solaro reaches the desired area, the scientific mission can be performed by docking the payload cab on the desired target. The motion of the 2 degree of freedom payload cab is infrared remote controlled. The payload cab can accommodate instruments like a MiroCam, an APXS, and MIMOS with a total mass of over 1 kilogram. On hard, rough terrain with stone height under the wheel radius of 75 millimeters and slope under 30 degrees, the breadboard has no motion problem. The breadboard is energetically autonomous during the 4 hours around noon on a sunny day. The solar power is between 20 and 30 watt as a function of the solar panel inclination, and the power consumption is between 15 to 55 watt depending on the slope and rotation angle. The energy balance on the Earth is positive if the mean slope is under 15 degrees. On Mars, gravity and sun power is different than on Earth. The calculation done with the Solaro simulator and with the field test experience show the same positive energy balance on Mars. Maximal slope climbing depends on the terrain and tire technology. It is approximately 15 degrees in thin sand to 35 degrees on a stony surface with normal tire. Other wheels must be developed to cope with the Mars surface. The Solaro breadboard has a limited obstacle avoidance system based on 2 ultrasound sensors. These sensors cannot be used on Mars. However, the objective of this very simple system is to show how an efficient locomotion structure helps to simplify the task of the navigation system. The sensor detects only obstacles over the wheel diameter and avoids them by turning left or right. The Solaro, thanks to its passive structure, can overcome high obstacles in relation to wheel diameter and rover weight. Low weight lowers energy consumption and enables a fully solar-powered vehicle. This capability leads to a high mean free path. This structure offers better efficiency compared to active designs such as legged rovers, while not suffering sensible reduction of climbing abilities. This allows exclusive use of solar cells for the rover operation and locomotion. However, the integrated solar power generation restricts the operation time and power to specific day times. Limited power storage should be used in specific cases like a shadow motion operation, transmission, and hard obstacle climbing. In conclusion, the reduction of power consumption for locomotion allows this rover to be small, light, and operational during more than 100 Martian days. The total mass of about 10 kilograms and its locomotion performance in comparison with actual rovers leads Solaro to become the perfect candidate for long-range missions on near-Sun planets.